let me welcome everyone to this quick talk. So quick talk, this is quantum information and coherence talk. The half of the talk at least is supposed to be at the tutorial level so that people who are planning to get into this area have something to get from these talks. And the remainder half will be the more of a technical nature. So the speaker we have today is Professor Stephen Walborn from the University of Concepción. Is that Concepción, or how do you say it?
Yeah. Concepción.
Concepción, okay. Concepción from Chile. Professor Walborn got his master's and PhD degree at the Federal University in Brazil. And he did his work under the supervision of Professor Carlos Monken. Again, Professor Monken is kind of a big name in spatial entanglement and stuff. He later then did his postdoc at the Federal University of Rio de Janeiro, Brazil, and where he became a professor in 2007 and stayed there until 2019. And in 2019, he just said that right before the pandemic, he has moved to University of Concepción, Chile, where he is, I think, almost setting up his lab and will start doing some fantastic stuff in the lab. So his research work focuses mostly on entangled photons and their use in studying quantum mechanics and quantum information. So the title of today's talk is Boosting Entanglement with Partial Coherence, and we are really looking forward to this talk. So over to you, Professor Walborn.
Okay. Thank you, Anand. Yeah, so let me say again, thank you very much for the invitation. As I mentioned, I'm really excited to give this talk, especially to you and your group. Yeah, so as you mentioned, I recently moved to Concepción, University of Concepción in Chile, where there is already a quantum information, quantum optics group led by Professor Gustavo Lima and Professor Esteban Sepúlveda. Here in Chile, we also have something called the Millennium Institute for Research in Optics, which I'm also now a part of. So let's see, there we go. So I'm assuming the slide just changed, correct?
Yes.
Okay, good. So here's just a brief summary of what I'll talk about today. And so as Anand mentioned, the first half of the talk, it will be more kind of introductory. So I'll talk kind of superficially about spontaneous parametric down-conversion and how you can use it to make entangled photons, and in particular, spatially entangled photons. Then I'll briefly review with what I call partially coherent spontaneous parametric down-conversion, in which the pump beam used in this nonlinear process is no longer a coherent beam. Then I'll talk about a particularly interesting kind of partially coherent beam known as the twisted Gaussian shell model beams. And then finally, in the last part of the talk, show how we use these twisted Gaussian shell beams to kind of change the entanglement properties of the photons in down conversion. Okay, so this hopefully is a video that's playing for you. So this video was made probably almost 20, well, maybe more than 20 years ago by my colleague Paulo Soto Ribeiro. I apologize for the resolution, but I like it because it gives you kind of the general overview of the most simple experiment in parametric down conversion. So the idea is you have a nonlinear crystal here, and you shine a pump laser. Typically, it's a laser in violet or ultraviolet laser, not always. And so every once in a while, as the photons or a photon in this pump laser enters the nonlinear crystal, and it's absorbed and re-emitted in this parametric process in producing two down-converted photons. So these are two photons that have roughly half the energy of the initial photons, so that the energy is conserved. Of course, it's not exactly half, but it's because of the phase matching conditions of the crystal, it's on the order of half. And so these photons are emitted in certain directions, which are determined by certain properties of the crystal and so on. And the point of these experiments is that when what the events we look at are called coincidence events. And so this is when we place detectors here in a certain position, And we look for the events in which one photon hits each detector at roughly the same time. So within a small detection window. And so when that happens, we look at the events and study them for whatever we're interested in. So the main point here is that by isolating these coincidence events, we isolate essentially the two-photon state. So this is a probabilistic process. So most of the time, nothing happens in this nonlinear crystal. The pump laser passes right through it. But every once in a while, with the efficiency of about 1 in a million, roughly, one of these photons, pump photons, produces a pair of down-converted photons, and those are the only events we consider. So this is important because we essentially remove the vacuum from the equation. So parametric down-conversion has been used for, I guess, basically 50 years, has been studied for about 50 years. And within, say, the past 20 or 30 years, it's been extensively studied because it allows you to produce correlated photons and more specifically entangled photons. And so there's a number of different degrees of freedom in which you can choose to work. So the talk today, I'll talk about spatial entanglement. And so even within spatial entanglement, there's a couple of different ways you can look at the spatial entanglement, including different paths of the photons or different momentum modes of the photons, different transverse modes like those with carrying OAM, orbital angular momentum. You can also study correlations or entanglement in temporal or frequency degree of freedom. So you can create different time bins or look at frequency time correlations. And of course, what's used quite broadly is polarization entanglement. And so to do this, you just need to use a slightly more complex source. There's basically two of them, and you can make these polarization entangled Bell states, and you have quite a bit of control on the amount of entanglement and high quality entangled states of 2 qubits. So just to mention a little bit more the spatial variables, or more specifically transverse spatial variables. So many groups have worked on this over the years. And so here's just a few ideas of the sort of things you can do. You can kind of discretize this. So of course, this transverse, we'll talk more about the transverse spatial degrees of freedom, but you can kind of discretize the momentum, isolating 2 different directions or 2 different positions, and create entangled photons in that way. You can look at the angular momentum correlations, which, as it turns out, angular momentum is conserved in the SPDC process, so the photons are emitted with correlated angular momentum. You can look at correlations in the angle and angular momentum of the photons. And more specific to the talk today, you can look at the transverse position and momentum correlation. So basically, you can imagine the photon as a point particle, and you can talk about its position momentum just the way we talk about position momentum of a point particle in non-relativistic quantum mechanics. And so an interesting thing is that there's now, for about the past 10 or 15 years, you have these cameras that are available, which can actually image the correlation single photons, and more importantly, you can detect the correlations of these single photons. And so here's a picture of a paper from about 10 years ago showing the position correlations of a pair of photons. So the transverse spatial variables, of course, which I'm referring to, which I call position and momentum, and I'll use these words position momentum kind of interchangeably with near field and far field. So the idea here is that if you have a plane here, like a source plane, and so you have a certain field amplitude on this plane, we can, if we put a point detector on this plane and that detector clicks, we can associate that with a projection onto, say, an X eigenstate onto an X eigenstate. If we perform, say, a Fourier transform, either by free space propagation or some sort of optical lens system, we can look at the Fourier conjugate plane to this near field plane. So this is what I've referred to as the far field. And if we do the same thing, we put a point detector in this plane and we detect a photon, we can associate that with the momentum degree of freedom of the photon. And then, of course, this is because we know that via the Fourier transform, the position here in the Fourier plane is related to the angle degree of freedom, or the transverse momentum degree of freedom here in the near field. And so the interesting thing here is that these near field and far field variables, position, momentum, obey, they don't commute, and they have a commutation relation that's very similar to position, momentum in quantum mechanics. And of course, they obey very similar uncertainty relations as do position, momentum, where you have some constant which depends on essentially the wave number. Of course, here, in order for this description to be valid, I mean, in order to talk about fields on these certain planes, typically there's a few approximations. One of them is the paraxial approximation. So we assume we have a field that's propagating like a beam. It's not diverging too much. And also the field is monochromatic. So we're not worried about the frequency. We're essentially fixing the frequency in some value. So so how do these spatial correlations arise in down conversion? Well, so here's a diagram I tried to make where, we have the laser beam coming in here on the crystal. And so the transverse momentum in down conversion is conserved. And so what this means is that if the photons will leave the crystal at equal but opposite angles in relation to the pump beam. So these two red arrows show possible emission directions of the photons. Of course, if one of the photons, say photon 1 is emitted, say, out of the planes above the pump field plane, of the other photon will be emitted below it. And of course, if photon 1 is emitted below it, photon 2 will be emitted above it. So you have these correlated momenta, and so any angle relative to with the frequency is fixed, these angles are equal in amplitude, but you have this azimuthal freedom. So that's why you have this emission cone of the down-converted photon. So here's a photo that my colleague Danielle Tasca took in the lab a few years ago, just using a really in the far field. Hello, I think, can you hear me?
Looks like it got disconnected, but let's.
Hello.
Hello. Can you hear me?
Hello. Yeah, I guess my internet cut out.
Okay, let's try again.
Yeah, I don't know what the last. Let's see. You can see the screen?
Yes. Yes.
Yeah, okay. I don't know what the last thing.
I think it was like. I think it was a slide before this.
Okay, this one.
Yes. Yes.
Yes. Okay. Yeah. So so I'm not sure where the transmission cut out, but what I was saying is that you have these correlated or anti-correlated emission angles of the photons from the crystal. And so when you look in the far field, this gives you this anti-correlation. So if you put detectors in the far field relative to the crystal, you should see the photons in equal but opposite angles. So you see you detect photons around this emission cone in SPDC. And so this, of course, and this arises from the conservation of the transverse momentum. In the near field, we have correlations as well. And this comes basically from the fact that the two down-converted photons are, if you allow me to use the word, born from the same pump photon. So this means that when one of these pump photons is destroyed and these two down-converted photons are produced, they're produced at the same position. And so This means that if you look at the source plane, or if you look in the plane of the crystal, you have position correlations. So if you could image this crystal plane onto a pair of detectors, you would detect photons at the same position. So this gives us a position correlation or near field correlations and far field anti-correlations. And so you can use these near field and far field correlations to identify entanglement, or to confirm entanglement or witness entanglement. So the idea is that if you scan your detectors around in the near field and the far field under typical conditions, what you'll see is these probability distributions of the two-photon detections, and they'll be given by these kind of Gaussian, elliptical Gaussian shaped things. And so the point is that the width here, since the photons are correlated in the near field, the width of this ellipse along this direction will be quite narrow. And since they're anti-correlated in the far field, the width of the ellipse along this direction will be quite narrow. And then you can use a number of different entanglement criteria to confirm that these correlations in the near field and far field are sufficient for entanglement. And so here's an example. Essentially, if you show that the product of these widths is less than 1, you can confirm entanglement. And so this was done nearly 20 years ago in Rochester by John Howell and Bob Boyd's group. So yeah, so kind of these simultaneous correlations in both the near field and the far field, which are conjugate planes in terms of in the related view of Fourier transform, are responsible for entanglement of the photons. So there's of course quite a bit more you can do with the spatial entanglement. A number of authors have done work on theory of down conversion, and so with the goal of describing the two-photon state. So under, let's say, typical conditions, the two-photon quantum state can be written like this. So it's here, these kets here are single photon states, right, with well-defined frequency. We're always going to be talking about a monochromatic approximation. And these Q1 and Q2 are the transverse momentums. So these are single photon states with transverse momentum Q1 or Q2. And so the possible allowed momentum of the two photons is determined by this function phi, which is the joint amplitude of the photons. And so, of course, if the key property of this function phi is that it's not separable, meaning that you can't describe it as the product of two functions, alpha Q1 and beta of Q2. And so since this is a pure state and you can't describe this function in a separable way, this means you have an entangled state. And so you can derive what this function phi should look like. And so Carlos Molking, in collaboration with Paulo Ribeiro and Sebastián Padua in 1998, showed that you can write this function phi as a function of, or as a product of two functions. So the first of them is this function v, which is the angular spectrum of the pump beam. So this is the wave vector distribution of your pump field. And the interesting thing here is that the argument of this function is now the sum of the two momenta of the down-converted photons. The other function that appears here is this sinc function. Sinc is just sine of x divided by x. And this is known as the phase matching function. And so this function essentially depends on the wave number and the length of the nonlinear crystal. And so you have these two different functions that describe the two-photon state, and these are functions that you can manipulate. So there's a number of different things you can do to manipulate this quantum state. And of course, like the key and kind of what I think is a beautiful feature of down conversion is the fact that this pump beam angular spectrum is now passed on to the two photons, and done so in such a way that it's passed on to the correlations. And so a really nice way to see that is through this experiment that Carlos Molking did back in 1998. And so this is just an illustration of the experiment. What they did was they put a mask in the pump beam. So this is just the typical down conversion setup. They put an aperture in the pump beam, and they imaged so this is the letter F. They imaged this letter F onto some plane out here where the two detectors are placed. So if you look at the pump beam, you see an inverted image of the letter F. And so they have these two detectors here, and they're going to detect the down-converted photons. And so if you scan detector 2 around in this plane, illustrated by this square here, you will just see a kind of part of the down-conversion cone. So of course, if the frequency is fixed, you're just going to see this cross-section of the cone. However, if you look at the coincidences, so if you just look at the events where you detect a photon at this position, rho 1, while you scan this detector around, this detector D2, you recover the image F that was in the pump beam. So as the equation showed, this information that's in the pump beam is passed on to the two-photon correlations. So this is, of course, quite nice because it gives you a way which you can do kind of, say, quantum state engineering. So this is something that, like in my scientific career, we've done quite a bit. So when I was a PhD student, we pumped the crystal with different Hermite Gaussian modes, which have different spatial parity, and we're able to control the interference of photons in two-photon interference. Later, we also pumping the crystal with Hermite Gaussian beam, we were able to produce kind of a novel quantum state that had some nice properties, such as genuine non-Gaussian entanglement. If you know about orbital angular momentum, if you look at these figures are the two-photon correlations. So you'll see these images that look kind of like these Laguerre Gaussian modes with this singularity here in the middle, and actually show that this is kind of the two-photon equivalent of a non-local phase singularity like you have in these OAM modes. And this state actually has correlations beyond entanglement, a correlation known as quantum steering. So just by doing something very simple, sending a Hermite Gaussian beam onto the nonlinear crystal, we're able to study some interesting things. So all this which I've described considers a pump beam that is coherent. So and of course you can describe the pump beam using the angular spectrum or the field profile as a function of the position R. And when you do this, you have this quantum state, which we talked about here on the right. Of course, the idea is that, well, what if the pump beam is no longer coherent? What if it's a partially coherent pump beam? In this case, we can no longer talk about the angular spectrum of the field profile. Now we have to talk about either, say, a cross-spectral density function or equivalent of Wigner function, and these two things can be retrieved from the others. I mean, so if you know one, you can calculate the other. Equivalent descriptions of a partially coherent beam. And of course, what you expect is that if you now have, since this properties of the pump beam are passed on to the two-photon state, it's of course intuitive to think that this would now produce a state that's no longer pure, but now mixed. This partial coherence is going to pass on to the two-photon state. So this is, of course, quite interesting. This coherence could be another parameter for state engineering. There's questions about the entanglement, and there could be some interesting scenarios that arrive from this partial coherence. So a number of authors, including Anand, who worked on this over about the past 10 years. Yeah, so there's some of these, there's several theory papers and several experiments studying what this two-photon state looks like as a function of the pump incoherence. So let me show you, this is one experiment that was done recently, which I present here because it has some really nice images of the two-photon correlations and also the pump beam. So in this paper, they use what's known as a Gaussian shell model light source. So it's kind of your typical incoherent Gaussian beam. And so this is what the pump beam looks like. They have a laser beam and they use rotating ground glass to introduce spatial incoherence. So this is what the pump beam looks like as a function of the incoherence. And so when they look at these near field and far field correlations, what they see is that, well, of course, as you would probably assume, in the far field, these correlations are lost. So when the pump beam is quite coherent, you have these nice correlations like we saw before. And then as you introduce incoherence into the pump beam, these correlations now are spread around. So that's what happens in the far field. In the near field, on the other hand, the correlations are more or less constant as a function of the incoherence. And this is because since the two photons these near field correlations come from the fact that the photons are born at the same part of the crystal, it doesn't really matter whether the pump is incoherent or not. I mean, the correlations arise from just the simultaneity of the production of the photons and not from the characteristics of the pump beam. And so in this paper, they look at this type of an entanglement criteria. And so of course, because this momentum correlation, the width is now going to increase quite a bit as a function of the coherence length, or as a function of the inverse of the coherence length. These you no longer violate this type of entanglement criteria. So here they calculated and estimated the Schmidt number, which is an entanglement quantifier for this type of state, and you can see that this number goes down quite a bit as a function of the inverse coherence length. So the kind of the take-home message here is that this the partial incoherence introduces a loss of spatial entanglement, and this is of course quite intuitive and what you would expect. So let me briefly discuss a little bit about partially coherent beams or partially coherent light sources. So as I mentioned, you have to use slightly more sophisticated tools to describe them. So one way you can describe a partially coherent beam is through using the cross-spectral density. So this is the cross-spectral density for what's known as the Gaussian shell model. So you can see that you have this Gaussian, so R and R prime are two different positions here in the transverse plane of the beam. And so the cross-spectral density is going to be a function of these two positions. So you can see we have a Gaussian function here as a function of R and R prime times. And so that's separable. It's a product of a function of R and a product of a function of R prime. But then you have this other Gaussian function here, which describes the degree of coherence. And this parameter delta here is given by is called the transverse coherence length. So you can, of course, this is the delta is really only meaningful when you compare it to the width of the Gaussian beam, which is given by this parameter sigma. So you can define what's known as the normalized transverse coherence length beta using this function here, so that beta varies between 0 for complete incoherence to 1 for complete coherence. So this Gaussian shell model, if you look at the intensity, it's just a Gaussian function. So let's say back in the early 1990s, Simon and Mukunda introduced a family of beams, or kind of more general partial coherent beam. Of course, this Gaussian shell model is a particular model. There are many different examples of Gaussian incoherent or partially coherent beams. And so one of them that's quite interesting is this twisted Gaussian shell model, which they introduced in this paper here in 1993. So what the question they were asking is, what is the most general class of Gaussian beams that are axially symmetric, meaning that you can rotate them around the central propagation axis and the intensity distribution is invariant. And so in answering this question, they discovered, I guess, this twisted Gaussian shell model beam. And so the cross-spectral density function is given by this function here, where now I changed notation from R and R prime to R1 and R2, but I think it's obvious. So you can see the first part of the function here is just like the Gaussian shell model, but then you have this extra term here, which is complex. And so this term here is known as the let me say this parameter u here that appears in the exponential is known as the twist phase. And so as we'll see, this exponential here is responsible for cross field correlations between near field and far field variables. So this part here is what gives this beam the twist, and so I'll show you what I mean by that. So if you look at the intensity distribution, this beam looks just like it's a regular Gaussian beam. So this complex term, of course, doesn't appear. So let me first talk about this twist phase. So this parameter u that appears in this function, in order for this beam to be physically, or for this cross-spectral density function to be physically acceptable, to be non-negative definite, the twist phase is limited by these parameters here. So essentially, you can see it's limited by the inverse of the square of the coherence length. So this means that if you have a perfectly coherent beam, so in which delta would be infinite, the twist phase must be 0. So this twist phase is quite distinct. It's not the usual phase which we talk about in optics. It's a phase that appears only in partially coherent beams, and the magnitude of the twist phase, of course, grows with the incoherence. So it's quite interesting in that regard. So shortly after so Simon and Mukunda published a series of papers about this, and then around shortly thereafter and around the same time, Freiberg and collaborators produced one of these beams in the lab. And so the way they did this was they exploited this convex decomposition in coherent beams. So essentially they produced coherent Gaussian beams that were mutually incoherent. And so each of these beams were displaced, say in the y direction. So the beams are represented by these ellipses here. And so they're displaced in the y direction, and then they have a linear phase that's applied. And the linear phase is represented by these black arrows. So you can see that the direction and magnitude of the phase depends on the position of the center of the Gaussian. So essentially you see that you have this correlation between the linear phases, of course, giving it a linear momentum. So you can see this correlation between the far field variable. So this would be like a QX represented by this arrow here, correlated with the near field variable y of the in the near field variable y. So this so then you can see, okay, what does this position dependent linear phase, what does this do to the beam as it propagates? And so when you study this, you can see that this makes the beam rotate. And so this is why these are called twisted Gaussian shell model beams. So these beams are partially coherent, and they have this rotation as the beam propagates. And so this was the first demonstration of these beams in the lab. Since then, there have been a number of papers producing these beams, many of them using this sort of decomposition here. And the kind of main point I want to emphasize here is that you have in these beams, you have these correlations between the near field and the far field variables. So because these beams are Gaussian, you can completely describe them in terms of what's known as a covariance matrix. So this is just the matrix of the second moments of the beam. So by second moments, I mean these second moments of the near field and far field variables. So the general description of a covariance matrix is given by this. And so if you choose the proper origin of your coordinate system, this covariance matrix describes completely the Gaussian beam. So all we need to describe the Gaussian beam, we just need to specify what these second moments are. So for the twisted Gaussian shell model, this covariance matrix is given by this matrix T here, where most of these parameters I've defined. Sigma is the beam width, R is the radius of curvature, U is the twist phase, K is the wave number, and this parameter tau squared here is the variance in the momentum degree of freedom, which is given by this function here. So what I want to call attention here is are these correlations that appear between the near field and far field variables between position and momentum, which depend, of course, on the twist phase or proportional to the twist phase. Another way in which the twist phase appears in this sort of beam is through the momentum variance. You can see that we have this term U squared sigma squared here, which makes the beam diverge faster as a function of the twist phase. And this is a characteristic that has been used to characterize these beams experimentally. If you want to calculate, say, the Wigner function of this beam with the covariance matrix, there's a simple recipe to do so. And another interesting property of these beams is that if you calculate the normalized transverse coherence length, it's also given by this factor beta. So just like the Gaussian shell model beam. And of course, if you set U equal to 0, you recover the Gaussian shell model. So our idea, so now I'm going to talk about what we did with these ingredients. So our idea was basically, well, what happens if we use these different types of partially coherent beams to pump the nonlinear crystal in down conversion. So this is kind of this is an illustration of what we wanted to do. So so in order to do this, what we did was we calculated the Wigner function of the two-photon state. And of course, as I mentioned, you can work with the cross-spectral density or the Wigner function. We chose to work with the Wigner function because it's very easy to obtain the Wigner function from the covariance matrix and vice versa. So with several approximations, which are kind of standard in the field, we were able to show that the Wigner function in terms of these global variables. So here I define these variables xi plus and minus, which are functions of the near, so it's just this 4 vector of the near field and far field variables, but in terms of the sums and differences of the variables of the individual photons. So I'll refer to these as global variables since it involves sums and differences of the local variables of each photon. So in terms of the global variables, the Wigner function factorizes into a product of two Wigner functions. And so the first one, W plus, is actually the Wigner function of the pump beam. And the second function, W minus, is the Wigner function of the phase matching function. So of course, all the partial coherence or all the properties of the twisted Gaussian shell model are going to enter in this function W plus, and then the phase matching function, which was that sinc function, is going to enter into W minus. So so in our work, the phase matching functions I mentioned is a sinc function. So you can approximate it by this here. Of course, you can calculate the Wigner function of this if you want, and so on. What we did is we use this, what's known as the double Gaussian approximation. So we approximate this function here by a Gaussian function. Actually, we approximate it by a Wigner function that's a Gaussian function. And I say double Gaussian function because we have one Gaussian describing the difference coordinates x and y, and one the difference in the position coordinates, and another Gaussian describing the difference in the momentum coordinates. And we have different widths for each of these, and these are not transform limited. So this is again approximation to this sinc function, but as several authors have shown, this approximation allows you to reproduce a lot of the interesting results. And the main thing is that you can do you can get a lot farther analytically with this approximation, which is why we did it. When you do this, you of course pay a price in this approximation, and that's in terms of the purity of the state. So since we have these widths differently, and we relate these widths to the individual near field and far field distributions of the sinc function. These, and I mentioned these are not transform limited. This means if we were to calculate the purity of this Wigner function, which is given, we end up with this function here, which for typical parameters is much less than 1. Okay, and so the reason we do this approximation is because we want to be able to work just with Gaussians. We want to be able to work with just the covariance matrices. And so the idea is that, well, we have these two Wigner functions, and we're now going to describe them both with Gaussian functions. And so we can either specify the Wigner functions W, or equivalently, we can specify what the covariance matrices are and work only with the covariance matrices, which simplifies things quite a bit. And for the phase matching function, from our Wigner function from the last slide, we have the covariance matrix is this diagonal matrix here with the widths as the elements along the diagonal. So now with that, we have a really simple description of the two-photon state that leaves the crystal. It's given by this covariance matrix. And so V plus and V minus are the covariance matrices describing the twisted Gaussian shell model pump beam, and also that Gaussian Wigner function describing the phase matching function. Of course, so this is what we have in terms of the global variables. We want to describe the correlations in terms of the local variables. So in order to do that, we want to calculate this matrix here, which you can calculate quite easily. And the different elements of this matrix here are functions of the elements of the matrix in the top row. So this is just a simple coordinate transformation. And I guess I should highlight these. So these covariance matrices here are 8 by 8 dimensional matrices. And so in each of you have these 4 blocks of 4 by 4 matrices. And so the matrix V12, you can of course identify what the meaning of these different 4 by 4 blocks. So the first block A are actually the second moments of photon A or photon 1. The lower block here, B, describe the second moments of photon B or photon 2. So these are kind of the local second moments of each photon individually. And then the matrix C here describe the correlations via the covariances between photon 1 and photon 2. So this, of course, simplifies a little bit our description. So we're going to look at these different matrices individually. So, okay, so since we now, so the ingredients here, we have this description, and then we have, we know what the covariance matrix is for the pump beam. We know what the covariance matrix is for the phase matching function. We just plug those into this description, and out pop these 4 by 4 blocks. So in terms of the single photon covariance matrices, they're equal. And so I present here just one of them, matrix A. So it's given by this. And so I just want to call attention to the fact that you see this, you have a similar twist phase term that appears here along the, in the near field, far field correlations. And so you can see that this is actually equal to half the twist phase that was in the pump beam. So each individual photon carries half the twist phase that is carried in the pump beam. And so in this regard, the twist phase is kind of conserved between the 2 photons. Of course, the most interesting thing here to look at are the correlations. And so here, this is an example of what the correlation matrix C looks like. And again, you can see that along the anti-diagonal, you have these near field, far field correlations. And these are correlations between a near field variable of one photon and the far field variable of the other photon. So again, it's correlations that are non-local meaning that there are correlations between position momenta of different photons.
One quick question.
Yes, please.
So is there, or how do we understand that why does the twist phase get divided into 2 equally between signal idler? I mean, it has to conserve the twist, but it need not be half, right? So are there possibilities that it could be 1/4, 3/4 kind of?
Yeah, that's a great question. Here it's half because I guess I did not mention this and I apologize. We're assuming a degenerate case. So the photon, each photon has twice the wavelength of the pump. So that gives you this 50-50 split. If you can see there's this multiplying the twist phase. If I go back a slide, is this is K, which K over 2 is essentially the wave number of the of each individual photon. So if we had different different frequencies, we would have different factors here.
Okay, that makes sense. Thank you.
Yeah, that's a good question. Thank you. Yeah. So I'm sorry. I apologize. I should have mentioned back in the beginning. We're considering the case, the degenerate case, in which the photons have the same frequency, which is exactly half the frequency of the pump beam. So yeah, so we have these matrices, and so with these matrices we can completely describe the 2 photon states. So we can calculate entanglement and so on, which we'll do in a slide or so. Before I do that, I just wanted to mention a nice aspect of this description is that you can calculate the purity of the 2 photon state. And since the Wigner function factorizes in this simple way, and of course this factorization is of course occurs because we have this degenerate situation of the frequencies. So the purity is written by the product of purity. So this would be the purity associated to the phase matching function times the purity associated to the Wigner function of the TGSM covariance matrix, or excuse me, the TGSM covariance matrix. And so since this U plus is just given, as it turns out, is just given by the normalized coherence length of the pump beam. So what I think is a nice result is you can show that the purity of the two-photon state is proportional to the coherence, the normalized coherence length of the pump beam. And I should mention that this result is valid even outside of this double Gaussian approximation. It depends essentially on the factorization of these two functions and the fact that the pump beam is this TGSM beam. So what this means is we can directly relate the mixedness or the purity of the two-photon state with the coherence properties of the pump beam. So what we wanted to do then is calculate the entanglement of the two-photon state. So the way we—
Another quick question, if that's fine.
Please.
Okay, so here you're saying that the purity of the two-photon state, this is determined by the transverse coherence length of the pump beam.
Yes.
So if I mean the transverse, I mean it's like the transverse coherence length of the pump is kind of just like you showed earlier, it kind of gets transferred to the two-photon state, and that's how it kind of determines its purity. But that transverse coherence length will increase as a function of z, right? Propagation distance. So this
Yes.
purity then increases as a function of z.
Well, as the transverse coherence length increases a function of z, but the normalized transverse coherence length does not, because it depends on the ratio. So both sigma and delta both increase by the same factor. I see.
Okay.
Yeah.
Okay.
Yeah. So beta is propagation invariant.
Okay. So in some sense, then this is like basis invariant. I mean, at least Z invariant measure of purity of the two-photon state.
Yes. Yes.
Okay. All right. Thank you.
Okay. Thanks. Yeah, please, in general, if you have questions, I don't mind being interrupted. I would rather we discuss the results. As I mentioned, I'm quite excited to present these results to the group. Yeah, so we have this relation for the purity, which we're going to use in a few slides. So we wanted to look at, of course, the reason we're talking about the purity is we want to look at the entanglement properties of the two-photon state, and also the purity of the two-photon state, or better yet, the entanglement is a function of the purity, which will be related to the coherence, the transverse coherent length of the pump beam. That's why we're introducing this term. So in order to evaluate the entanglement, we used this positive partial transpose criteria. So this dates back to 1996, where Astro Perez and one of the Horodekis showed this for discrete systems, and Simon also showed this for continuous variables. So that I'll mention this in a little bit conceptual, because it's a quite beautiful and simple idea to understand in terms of entanglement. So the main idea is that a general description of a bipartite separable state is given by this here. So it's just a convex sum of density matrices for systems A and B. Here, lambda is a non-negative coefficient, which would sum to 1. So if you consider the partial transpose of this state, so partial transpose means I do the transpose of one of the systems. So say system B. So if I transpose all the states rho Bj here, this is still going to be a physically acceptable state in the sense that it has, say, all non-negative eigenvalues. And this is because this the transpose is a physically acceptable process. And so if the transpose of rho Bj is a physically acceptable process, then the convex sum is also a physically acceptable process. And so if I take a state, rho AB, and I do the partial transpose in system B, and then I discover some non-physical properties. Say, for example, I discover this state has negative eigenvalues. The transpose state has negative eigenvalues. Then this would imply that the state rho AB cannot be written in this form that I have above here. So this means that rho AB cannot be a separable state, and if it's not separable, then it must be entangled. So this is the idea behind the this positive partial transpose criteria. So in terms of continuous variables, there's this nice paper by Simon in which he shows how you can do this for a bipartite continuous variable system. And in particular, if you know the covariance matrix of the system, you can do the partial transpose in a really simple way. All you do is you invert the momentum of system B. So here in our case, it's you invert the momentum of photon 2 just by multiplying the covariance matrix with this matrix T here to do this inversion. And then what you have is the covariance matrix of the partially transposed state, and then you look for some non-physical property. So what you can do is you can find what are known as the symplectic eigenvalues of this matrix. So you do some matrix multiplication and look for eigenvalues. And if these symplectic eigenvalues are less than 1/2 in terms of our coordinate system, this would imply entanglement. So essentially, it's the same idea. You're looking for a condition which would show that this partial transposition led you to a non-physical covariance matrix. And so that's what we did in terms of the scenario we're considering with the twisted Gaussian shell model beam. So here, this graph shows, this is from a paper we published. It shows the smallest symplectic eigenvalue as a function of the normalized coherence parameter. And so you can see when the coherence is close to 1. So I should mention each curve here corresponds to a different value of the twist phase. So the black is twist phase 0. The red is the maximum value of the twist phase. So it's the limiting value related to the coherence length. And blue is half of that value. So when the coherence is quite high, you can see in all these scenarios, your beam is entangled, or your two-photon state is entangled. As the coherence decreases, of course, you lose entanglement. These the smallest symplectic eigenvalue is greater than 1/2, and then of course as the coherence decrease of the pump beam decreases even more, you actually recover entanglement in when you have a non-zero twist phase. In this, which you can see in this leftmost portion of the plot. So, I mean, this shows that this non-zero twist phase can actually lead to entanglement, and more of it leads to entanglement in this scenario where you have very little spatial coherence or very little transverse coherence of the pump beam. So this is, of course, what led to the title of our paper and the title of this talk, was this idea of boosting entanglement with incoherence. And so you can see that you need quite a small value of beta here in order to see this. So I looked at some of the papers, experimental papers of partially coherent SPDC, and I think that a beta value of about 0.05 should be experimentally feasible. So these are theoretical results. They have not been experimentally produced yet, but I think that it should be feasible to show them. So do I have, can I talk 5 more minutes?
Yeah.
Okay.
Maybe I can ask one question if that is fine.
Please.
Okay, so this smallest symplectic eigenvalue is that taken as a measure of entanglement as to, whether it's increasing or decreasing? So can we have that kind of sense from this?
Yeah, so for Gaussian states, so of course our state is not Gaussian because of the sinc function, but of course every state has, say, a Gaussian representation, right? So there is a Gaussian state that has this same covariance matrix, right? So for Gaussian states, the small symplectic eigenvalue, for bipartite Gaussian states, this is an entanglement quantifier. So you can define kind of more well-known quantities like the negativity or the entanglement formation or other things, which are functions of this smallest symplectic eigenvalue.
Okay.
Yeah, and those quantifiers have some sort of physical meaning in terms of
strength of the
tasks and so on. Yeah.
Okay.
Yeah. So this is say not a witness. This is or not just a witness. It is, say, a quantifier. So this is kind of the main result of the talk that I wanted to present. And so I just have a couple more slides showing kind of more things that we did with this. So we also looked at, so this scenario here, which I show is for actually, in order to see this, you have to focus the pump beam quite drastically on the crystal. I mean, not unreasonably so, but it has to be highly focused. So here, here are some results showing what happens for different amounts of focusing. So these parameters here, sigma minus divided by sigma plus, are essentially the width of the phase matching function divided by the width of the pump beam. So so going from weak focusing into intermediate to tight focusing. So of course, these plots show the normal. This is different parameters. The normalized twist phase. So now it's just we just define the twist phase between 0 and 1, and this is the transverse coherent length of the pump beam on the vertical axis. So you can see that when you have weak focusing, the beam is essentially entangled for almost all parameters of beta and u, and you lose entanglement only when the coherence length is quite small. And you don't really see this. I mean, you see a little bit of blue down here below, so you do see this kind of a revival phenomenon of the entanglement as the coherence becomes quite low, but it's most likely not observable. In the case of tight focusing, of course, you can see that you have a light blue region above here where you would have entanglement for high coherence, and then you can see this this appearance of entanglement for larger values of the twist phase and smaller values of beta, of the transverse coherence length. So this is this region in which the entanglement is boosted, if you will, from the incoherence. And then for what I call intermediate focusing, you see the same sort of behavior, but slightly in a much smaller region. So of course, this is something that depends on these. To observe this phenomenon, you have, of course, have to work in a scenario where you have rather strong focusing of the pump beam. Another thing we looked at are the OAM correlations of this type of state. So we basically took we wrote the equivalent of we wrote the density matrix of these of the two-photon state with this TGSM pump beam, and we looked at what the OAM spectrum of the photons would be. And so we did this numerically, and I should say this is a qualitative numerical result in the sense that, I mean, you have to sum over many OAM modes of the individual photons. I think we worked in like a 70-dimensional space for each photon. So I think it was, I think 75-dimensional subspace for each photon, plus around 10 values for the radial index of the modes we use, which were the Laguerre Gaussian modes. So we have a description, like I say, a truncated description of the two-photon state. And this accounted for, I think, only, I don't remember the proportion, but it did not describe even the majority of the state, but it described the most prominent, the largest probabilities that appear. So this is what the OAM correlations look like when you have zero twist phase. So usually you would have OAM correlations along, in this graph, it would be along the diagonal direction. And because of the incoherence, these diagonal correlations are smeared along this direction. When you change the twist phase and you have a maximum twist phase, you have the same smearing of the correlations, but it's only smeared in one direction. So, and in this direction, it's this upper portion of the graph, upper right portion of the graph, and this is because we chose a twist phase that was positive. If you choose a negative twist phase, the minimum value of the twist phase, these would be smeared along the lower direction here. So I don't, yeah, I show this because I think it's quite curious, and we haven't really done anything interesting with this yet, but I think it's interesting how this OAM spectrum, the two-photon state, is quite different in the two cases. Yeah, so there's a number of say interesting questions I think that are here in terms of what are other interesting applications of twist phase, both in quantum optics, two-photon optics, and also classical optics. A big question is, okay, you have this highly mixed entangled state. This is, a curiosity and it's interesting, but is it useful for something? And can you do some sort of protocol, or can these correlations be used to do something useful? Of course, we would like to do experimental verification of this. In this, so the only experiment we've done in terms of in this direction, and this is on my last slide, I believe, is we studied a little bit stimulated parametric down-conversion with these TGSM beams. So what we did is we have this, so stimulated down-conversion is you have the usual spontaneous parametric down-conversion process, but instead of, but you introduce a second beam, so you have the usual pump beam, and you introduce a second beam, which is known as the seed beam. And so what we did in this experiment, which was actually done in Brazil, we use a coherent beam as a pump beam, and then we seed this process with this TGSM beam. And so what the seed beam does is it amplifies the emission of photon pairs. So along the seed direction, what you have is the seed beam plus the photon pairs that are produced in the down conversion process. And along the idler beam, you have two components. Actually, you have the spontaneous component, which is always there. Spontaneous down conversion is essentially stimulated down conversion, where the stimulated is by vacuum. And so in addition to the spontaneous component, you have the stimulated component, which is much larger. So essentially here, the outgoing idler beam is essentially the stimulated component. And so in this scenario, what we showed is that the idler beam is actually the phase conjugate of the seed beam, and it can also be described as a twisted Gaussian shell model beam. So, and so when you do this phase conjugation, you should change the value of this. You should invert the value of the twist phase, invert the sign of the twist phase. So in order to show that this happens, we did a couple of different experimental tests, and one of them, which we did, was we put double slits here in the seed beam and the idler beam, and we looked at what the interference pattern of the double slits looked like. And because of this this azimuthal phase, this twist phase that appears in the beam, you can, and of course we showed this theoretically, and then we verified experimentally. What you see is that the interference pattern rotates as a function of the twist phase. So so let me say, so these results in each square here of results, the ones on the right are when the twist phase is very small. So you can see that the interference pattern is essentially along the vertical direction. On the left side, you have results when the twist phase is larger in magnitude. So you can see that both the seed and idler beam the interference patterns rotate a bit, and that these the rotation directions are of roughly the same magnitude and in opposite directions. And so, yeah, and of course the rotation direction depends on the sign of the twist phase. So this is, so we did a little bit of quantification here, but it's mostly a qualitative result that the idler beam has the equal in magnitude but opposite in sign twist phase of the seed, showing phase conjugation. So this is kind of the first experiment we did with these TGSM beams, and this was done by my colleague Paulo Soto Ribeiro in Brazil. So that's all I wanted to present to you today. Here are some take-home messages. I mean, I hope I was able to convince you that this twist phase is quite interesting characteristic of these optical beams. I think this is really interesting. I think there's other things to do here. Of course, there's a whole lot of work in classical optics studying these beams and studying different propagation properties of these beams and so on, which I didn't have time to mention here. But there's quite a bit of literature about it. In our work, what we show is that by using these TGSM beams with this twist phase, we're able to see some interesting entanglement properties of the two-photon state and produce these highly mixed yet highly entangled two-photon states. And well, finally, I briefly mentioned this first work we did with stimulated PDC showing phase conjugation of these TGSM beams. And so one of the interesting applications of phase conjugation is you can kind of correct effects such as turbulence. And one of the applications for TGSM beams is in optical communications. So we think this could be interesting in terms of, say, correcting beams that suffer turbulence through propagation and so on. So I think that's it. Yeah, that's all I wanted to present, and thank you very much. And sorry for going slightly over time. Thank you.
All right, thank you so much. That was actually quite nice. So let me just open it up for questions. So if anybody has question, I have few, but I'll go next. So Abhinandan, yes, you just unmute yourself and ask a question.
Yeah, this is a very nice talk and very quite interesting area. So I have this question: why this EPR type measurement? Why it is not able to capture such characteristics when we decrease the coherence length, and still we are getting highly entangled states? So is there any physical reason?
Do you say EPR type measurement?
Yes, I mean this position correlation, momentum correlation measurements.
No, that's a great question. The let me just go back here. Yeah, so you can see this slide, two-photon correlations.
Yes.
So so this is the matrix describing, say, the correlations, and the main, so kind of the best reason I can say to you is that, so the main effect of the twist phase is to introduce these correlations between the near field variable of one photon and the far field variable of the other photon. So if you look at the standard EPR measurements where you measure near field of both photons and far field of both or far field of both photons, fail to take into account these correlations, since it's kind of the cross correlations of the two. So and so we tried to look for maybe a simple entanglement witness or entanglement criteria, like a modified EPR criteria, you know, say between near field and far field and some others. However, we were not able to find a simple entanglement criteria. So it's my belief that at least for typical experimental parameters, what you have to measure here are all the different elements of the covariance matrix. And yeah, that's but we did not do any, say, you know, strong numerical searches for simpler entanglement criteria. But I mean, it is possible that there are correlations that involve knowledge of all the elements of the covariance matrix.
Okay. And another question, is there any possible way to measure such symplectic eigenvalues experimentally?
Oh,
typically.
I have a follow-up question, Abhinandan, before you go to the next your question. I mean, the question is regarding the EPR. I mean, do we know that when you are seeing the boosting of entanglement through the symplectic eigenvalue, do we know for sure that the EPR criterion there actually fails and doesn't you know, show entanglement? Or I didn't get that.
So this here in this plot, yeah, so this plot, just for this particular example, this the dashed line here shows the EPR criteria, the usual EPR criteria. Yeah. So what happens, I mean, the reason this particular criteria is not violated is because, well, the near field correlations are always there. So the near field, so this near field variance is still quite small. It's just like in the usual coherent case. But the what happens is, because this is the variance of the far field, and actually this variance grows even faster because of the twist phase. So this this is the problematic term, just like in the usual say partially coherent SPDC with a Gaussian shell model B. So the same sort of it's the same sort of reasoning. The difference here is because you have these cross correlations, you have these other elements that now, or these other criteria that of course can be used. And I should say that even so, we have in our AVS quantum paper, we studied the case, for example, when you have just the Gaussian shell model beam, but you introduce phase curvature of the beam. And even then you have the same, you don't have this revival of entanglement, but you do have this sort of thing where maybe if you look at like from 0.2 to the right in this graph, you have the sort of scenario where the EPR correlations fail to identify entanglement. But if you look at the small symplectic eigenvalue, which would involve, say, more knowledge of the covariance matrix, you could still see entanglement. So this, I mean, this EPR criteria is a kind of, you know, it's not technically an entanglement witness, but it witnesses, it's an entanglement witness in the sense that, you know, it can see entanglement, but it's not, say, a quantifier.
Okay.
I mean, there are entangled states that do not violate this criteria.
Right. So then it means that, I mean, it's like you kind of like have found a basis in which if we look at, then we do see entanglement, while EPR type correlations, EPR type basis will not see entanglement necessarily.
Yes.
Okay.
Yes.
Okay.
Yeah.
Abhinandan, you go with the second question. I'm done.
Is there any possible way to measure this symplectic eigenvalues experimentally?
Yeah. So to measure them directly, I don't think so. But I mean, essentially, what you have to do, I mean, let's see, you essentially have to discover the elements of the covariance matrix. So which is, you know, not good news in our case, because we essentially have to discover the elements of this 8x8 covariance matrix in order to calculate them. Yeah. So I mean, there are we have not done this, but there are numerical, you know, semi-definite programming techniques you can use to try to search for better, you know, simpler entanglement criteria. So that would be, I mean, to do an experimental verification, that would be the first thing to do, to look for something that's simple. But I should mention that, so you have to measure these 8x8, this 8x8 matrix. But if I'm not mistaken, we figured this out. So if you have an EMCCD camera and you can measure correlations, this would involve essentially measuring correlations in 5 different sets of planes. So you'd look at, say, the near field of photon 1 with the near field of photon 2, the far field, the 2 far fields, and then you would have to look at cross correlations between near field and far field. And then you would also have to look at an intermediate plane. And so if I'm not mistaken, I think there were 5 different measurements you would have to do in order to calculate all these variances and covariances and construct this matrix. So it's, you know, more experimentally demanding than the usual EPR criteria, but it's not, you know, absurd amount of measurements.
Okay. And final question. In this, I think analysis, this beam waste of the pump is at the crystal plane. Is it true?
Yes.
So if it is not at the crystal plane, is there any effect of that extra spherical phase that will come up? Is there any effect of that on the lambda?
Yeah, that's a good. Yeah, no, that's a good question. And yes, yeah, here, so in the results I presented for the twist phase, we assume that the beam waste is at the crystal. We did, I mean, as I mentioned, the radius of curvature, of course, can also lead to entanglement of the beam. So, or excuse me, of the 2-photon state. So yeah, you have some sort of, so you have sort of 2 effects, a kind of entanglement that comes from the phase curvature and also from the twist phase. And these are combined in some way, which I'm not really sure. I can't really say anything more than that, but yeah, there's an effect.
Okay, thanks.
Thank you.
Okay, other question? Okay, I have one more. So for measuring the symplectic eigenvalue, I mean, for example, like for measuring EPR, I just need to measure, you know, point by point correlation for X and then P. But for measuring the symplectic eigenvalue, I guess one has to look at the whole beam, right? The whole 2-photon field. Is that correct?
Yeah. So yeah, you have to. So as you would have to measure. So here let me see if there's yeah. So here we have where do I have this written down? Sorry. Here. So so each photon has, say, 4 variables: the X and Y near field and the QX and QY far field. So because these are X and Y coordinates of the same photon, you do save a little bit in terms of your effort. So, I mean, when you measure the near field, you measure X and Y at the same time, right? So I'm assuming you can do, you know, actually 2-dimensional imaging of the transverse plane and not just a single direction, right? So yeah, so you have to measure the X and Y near field of both photons and the correlations, You would measure the X and Y far field of both photons and the correlations. You would measure one of them near field and one photon near field and one photon far field, and vice versa. And then you would have to measure both of them. So with that, you have all the cross photon correlations, but what you're missing are the let's say the cross degree of freedom single photon correlations. So you would have to measure say some an intermediate plane, like using the say a fractional Fourier transform to measure something that's neither position or momentum, but is somewhere in the middle.
Okay.
And then so with those, so you could do that, and those could be independent measurements of the photons. So you could, so I think in all there's 5 different coincidence imaging setups you would have to do. I don't know if that's
that's fine. No, so now you said that to see the boosting effect, it needs to be a really focused pump beam, right? So,
yes.
so if the pump beam is highly focused, then I'll have a very diverging two-photon state.
Yes.
Okay, but that will not make it difficult because here you are still doing the Rx type measurement. So Rx for the signal will become, we can keep it at 0 and then do a two-dimensional coincidence imaging. Is that the, okay.
Yes.
Okay.
Yeah.
Okay.
Yeah.
Okay, now final question, which is what you had also on the slide. I mean, so you had 2 questions on your slide, So what are the answers to those 2 questions?
In terms of, let's see, these questions.
Yes.
Yeah. Okay. So the first questions. So in terms of, I mean, the first question you can ask it, like I mentioned, in terms of classical optics or in terms of quantum optics. So in classical optics, there've been some work in this direction. I may have a slide, I'm not sure, but what's been studied with these TGSM beams versus this usual Gaussian shell model beams is how are they affected by, say, turbulence. So it's these beams, so it's kind of a tricky topic because these beams diverge faster as a function of the twist phase. So you have more divergence, but what they've shown is that in at least like the weak turbulence regime, the divergence induced by turbulence is less, relatively speaking, for the TGSM beam and the Gaussian beam. So there's some indication that these sorts of beams could be interesting for free space optical communications or something like this, or even some sort of remote sensing and things like that. So that's one particular application. Another application, there's been some work looking at using these correlations from the TGSM beam in kind of ghost imaging scenarios, which I unfortunately can't tell you too much about. But I mean, so there have been some proposals how you could use these correlations to do these interbeam correlations in order to do interesting things. And so like I think so kind of the first, in terms of in the 2-photon or the quantum optics scenario, the first thing I think that I plan on looking at is, okay, how this idea of the propagation through turbulence in terms of the 2-photon state. We should see the same sort of benefit. In terms of like the second question is this highly mixed head entangled state useful? I mean, to be honest, I don't know. So yeah, the work that what I would like to do and which I've thought about but haven't made any real progress is it devising some sort of, or finding some sort of protocol or some sort of scenario in which this state actually allows you to do things. And actually the way it's kind of, I think the maybe easiest path here is to look at the OAM correlations, which I said, and it's sort of it's a little bit tricky because like I said, the OAM correlations, you have to consider a huge state space. And so, but still, like even with these qualitative results I showed, you see this difference in the correlations. And I think that's maybe an easy, at least for me, that's an easier scenario to kind of play around with and think about, just because you have this kind of discretized correlations and so on. So yeah, so I mean, these are open questions, which I have some ideas about, but I don't have any sort of real conclusions that I can tell you. Yeah. And so, yeah, I put these questions specifically here. It's specifically for this talk to your group because, yeah, I think these could be interesting things to discuss, and maybe someone here has an idea, and I would love to see some sort of progress made towards these questions.
Yeah, so I mean, you kind of did mention that in the classical context. I mean, the classical context, what we have seen, I mean, there's several works showing that if it's a mixed state, that is usually, I mean, that has several benefits when it comes to either imaging or propagating through turbulent medium. So
Yes.
now here it's an entangled field, which is mixed. So any protocol based on entanglement will be useful only if the entanglement is high. And yes, if you're propagating through a turbulent medium, then you need mixedness. So maybe from that logic, will it not be that, you know, if you have an entanglement based application that requires photons to go through a turbulent medium, in that case, this mixed yet entangled state could be, you know, the answer?
Yeah, I agree. I agree 100% with the logic. I think that's probably true. Yeah.
Okay.
Yeah. I mean, I guess, yeah. What I think what remains to be done is to do some calculations and so on, and yeah, to support that intuition. Yeah, but I think that's completely true.
Yeah, that does seem, yeah, excellent. All right. Any other question? Excellent. I think we have asked you enough. So
thank you. It's thank you. It's a pleasure to present this work to your group.